did. So where I live is just like on this hill, and it's just seems like you're snowed in. But as soon as you get out of there, it's fine.
Yeah. My neighbor is like that too.
Same thing.
Yeah, very good car.
All right. Thank you. All right, I think that's gonna be it for today. I mean, these few people, everybody else is a little. That's fine. Portland drivers aren't the best students, so they're not the best in general. But anybody have any questions on the last week's homework that you guys just did? Yeah.
I had just one quick question. There's one of the questions said give the type of bonding in each of the following, and it was like BaCO3, and it said like the answer was ionic but covalent in the polar subatomic ion or atom.
BaCl3?
BaCO3.
Oh, CO3. Oh. Yeah. Okay.
So I was just had a question, like, I guess I did their like average electronegativity and then the change as all three of them individually, but are you supposed to do like Ba and then CO3 is a unit
So
separate?
yeah, this one's kind of funky because you can't really take the ion itself as a whole thing on the bond type triangle.
Okay.
So I think for this one you'll just have to recognize that carbonate is really an ion.
Yeah.
It exists as an ion. Barium is a pretty, it's way down there. It's really low electronegativity. This is pretty you can't argue that it's not ionic. It's pretty ionic. But if you break down this part, like that is put together using covalent bonds.
Okay.
So it's the compound itself is ionic, but it's got some covalent bonds in it.
Okay.
Put it that way.
Okay.
Can you show you what my question was?
Yeah.
So this one, I was wondering why it was this one instead of this one.
So what? Oh, position of compound tin iodide. Why was it B rather than A? So
I think I thought it was ionic.
yeah, well, so tin iodide. Tin is not the most electronegative metal, and iodine is not the most electronegative non-metal either. They're kind of in the middle. They're still respectively metal and a non-metal. Let's see. So when you consider, I mean, the A and B both have an average electronegativity somewhere in the middle, which makes sense. In terms of a difference in electronegativity, since tin, I mean, you can look them up even, but since tin is not really low, it's kind of somewhere in the middle, still metallic, but around 2, 1.8, something like that. And iodine is not really high, it's above 2, but it's close to that. It's like maybe 2.5, I think it is, something like that. The difference in electronegativity is going to be small. And so that's why A, since it's way up there, has a high difference in electronegativity. B would have a lower one.
Okay.
Actually, wait. AgCl. Sorry, I mean, I'm reading the question wrong. So SNI4 is there. What about AgCl? So I guess we're gonna have to look it up. Ag is gonna be slightly less electronegative than 10. Cl is gonna be, I guess A would be a slightly better choice, although that's a really big change. So I think the problem with A is that it's just a much, much bigger difference in electronegativity. I think for this one it would be best to look up the actual electronegativities and just kind of look as you look it up. Is that from the printout or is that from?
And so I think these values are slightly different. It's not from the word thing. They're slightly different because when I mapped the things later in the homework, I got them all in right areas, but my numbers were a tiny bit different.
So,
these are just close.
I mean, if you look at silver and tin, silver is 1.93, tin is 1.96, they're hardly any different. Chlorine and iodine are slightly more different, but, so I guess the average electronegativity is gonna shift to the right a little bit more, because while silver is not a little lower, it's about the same as tin. Chlorine is a little higher than iodine, so the average is gonna shift to the right some more. And then there is a slight difference, so I think, yeah, B is still a better answer because they're not that different.
Okay.
So for A, you'd have to have a really big difference in electronegativity, and you're not getting that with silver.
Okay.
Oh,
See, I can keep that
yep,
one now,
yep.
that was the method. Thank you.
I guess the takeaway from that particular problem is the transition metals are always funky. Like while we can look at the periodic table and gauge, oh, cesium is going to have a super low electronegativity because it's way down the left. When you get to the transition metals, you know, silver is one of them. It's not like you can obviously say, oh, silver is going to be lower than tin just because it's to the left. Because it's in the transition metal area, the trends don't really work super well.
Okay.
So we have to look them up. Yeah. Okay. Yeah.
I'm looking at the answer for the last couple problems. and
Okay.
It says 5 is E.
There could be a mistake. Let me see. 5. Which of the following has the highest metallic character? It says E. Oh, yeah, that's a mistake.
I think in the chemistry review, there's a bunch of questions missing answers.
Okay.
The assumption of 5 is actually 8 and I'm 1.
Okay. If you remind me to like look at those after class, I could try to go in and fix that. We've tried to make changes over the time, and then when we copy those changes to the next class, sometimes those changes make it, sometimes they don't. So I'm sorry if that didn't get fixed, but yeah, okay. Hopefully it worked out though. I mean, you understood the actual answer. Okay, so let's get back to what we were doing last time, and I can just show you real quickly. We were looking at unit cells, and these are basically the smallest representation of a pattern that repeats in a crystal structure. So we did practice with 2D structures. We did the penny thing. We have these definitions. Coordination number, this is the number of nearest neighbor atoms that are touching whatever atom you're focusing on. The coordination geometry is the arrangement of those atoms around that specific atom that you're focusing on. And so we did that 3x3 square of pennies. We found that even though that central penny is surrounded by 8 other pennies, there's only 4 that are closer than the others. So it's only got 4 nearest neighbors. All right, so we did that, and we had to call this, describe the shape. It's kind of a square shape. We'll get to the shapes, I think, a little later. Let's talk about something else that we can get from a unit cell that makes unit cells useful to us. All right, just describing what they look like. Why are we doing this? Well, one thing that's useful is something called packing efficiency. It's a measurement, or even a calculation, because this is pure geometry we're doing, of the total area of the cell covered by the area of the atoms within the unit cell. So we're still sticking to 2D right now, 2-dimensional. We'll switch to 3D later, because the calculations get a little bit difficult with 3D. But this is a unit cell. So imagine you have a field of atoms that are arranged like those pennies, and instead of drawing this, as big as you can to show, hey, it repeats all over the place, I'm just going to say, oh, well, here's a unit cell, and that particular pattern repeats everywhere. How do we know the unit cell works? You take that unit cell, and if you can draw the same unit cell adjacent, so right here, or here, and it's the same pattern in every single cell, then that's a unit cell. That represents the smallest possible way to represent that pattern. So just inside this box, that's the unit cell, not outside. So packing efficiency is, well, how much space do the atoms take up within that unit cell? So in order to do that, we need to think about it in geometric terms. We have the length of a unit cell, that's S. And the way we calculate the packing efficiency is what is the area of the atoms inside the unit cell, and what is the area of the total unit cell. And you divide those. Just a fraction, multiply by 100% to get a percentage. So for a square unit cell, it's not too hard. So we're going to do an example of that. Let's get to that. Actually, let's do that now. So let's do CT question 15 in chem activity, not 26, 24A. Another mistake for an older thing. So if you look at chem activity 3 or 24A, mine says page 32. I think yours may be 28. Yeah. Okay. Page 28 in yours. There's one question, question 15. And I think this is something we should do on the board because this is tough for people who haven't done geometry in a while. Let's calculate, so 15, build a body-centered arrangement of circles as shown in the diagram below. Note that the unit cell is outlined by a square box. All right, before we do that, actually, let's look at this example in a little bit more detail so we can understand what we're trying to do. Here's the example that was on the board. It's right above model 3. So to calculate a packing efficiency, let's first calculate the area of the unit cell. That's actually pretty easy to do. So how do you calculate the area of a box? It's just length times width. That's it. So if I say the length of one side of this box, this unit cell is S, and use a variable here, algebra, that's S, that's S. What is the area? S times S, S squared. Okay? So that's what's going to be on the bottom. Now, let's talk about the unit cell in terms of atom sizes. All right, so here's an atom. And we define the atom size usually with a radius, right? R, let's call it R. Well, what is the length of a unit cell in terms of the radius of an atom? So what is this length in terms of what our cell's radius is? 2R, yeah, 2R. So if I take two radiuses, 1, 2, that's the length of a unit cell. So instead of using the area of S squared, right, length of the side of a unit cell is S, so S squared is the area, I'm going to instead use 2R. 2R is the length of the unit cell. So if I square that, I get 4R squared. That's the area of a unit cell, 4R squared. So further, so good? So I've got the area of the unit cell in terms of the radius of an atom. And if you guys are like having your alarm bells going off, like, oh my God, we're going to have to do this in an exam, you're not. I am going through the derivation with you. This might be extra credit, but we need to understand the results of this, so it's good to go through how we get to it. Okay. Now let's talk about the area. So we have the denominator. We have the area of the unit cell in terms of the radius of the atoms, 4R squared. So how about the numerator, the area of the atoms within a unit cell? Well, this part of the atom is here, inside the unit cell. This part of the atom is inside the unit cell. This part of the atom is inside the unit cell. And this part of the atom is inside the unit cell. Let's make that a little easier. What proportion of the atom, of this particular atom, is in the unit cell? So if I take this atom, how much of this atom is inside the unit cell? A quarter of it. That's it. And so what is the area of an atom? So how do I do area of a circle? Anybody know? Pi r squared, right? So that's the area of one atom. Pi r squared. But only a quarter of that is inside the circle. So I can do divide by 4, and that's the part of that atom that's in the circle. But let's make it easier. How many quarters are inside this unit cell? 4 quarters. So really there's one total atom is inside the unit cell. There's 4 pieces, 4 quarters, but that adds up to 1 quarter, one total atom. So that's how much of the atom, how much atom is inside the unit cell, pi r squared. And that's where this comes from, pi r squared. So you do this calculation, what is pi r squared divided by 4r squared? Well, the r squares cancel, and I'm left with pi over 4. We multiply that by 100%, you get 79%. That is the packing efficiency for this arrangement of atoms. 74% of this square is filled with atoms. That means 21% of it is empty. That's what we're talking about here. That's how we're calculating this. So now we're going to do question 15. This is a different arrangement. So notice how the arrangement works. We call this a body-centered arrangement because there's an atom in the very center of the unit cell, and then there are atoms on the corners too. This is definitely a different arrangement than what we have on the board over there. So let's kind of calculate the packing efficiency now. Well, the area of the unit cell is a little different because it still is side squared, right? Side times side, that's the area, but we want it in terms of the radius. So, how do we get the radius? Well, it's not 2r anymore because there's this gap here. So we have to use Pythagorean's theorem now, okay? What is the length of the diagonal in terms of the radius of the atom?
4 of them, isn't it?
Yeah, there are 4 radiuses. There's this radius, 2, 3, 4. 4 radiuses. That's the diagonal. And if you guys remember Pythagorean's theorem, alright, Pythagorean's theorem says when you have a right triangle, which is what we have here, we've got a right triangle, there's the angle, there's the triangle. A squared plus b squared is equal to c squared. So the square of the 2 sides is equal to the long side squared.
Isn't it already telling us what the answer is? It says 1 equals 4, so.
So L, the length of the diagonal is 4r.
But there's 4, so it's just R1.
Well, so that's what C is going to be. C is 4r. C is the length of that diagonal. But I don't want the, what I want to do is I want to know what is the length of one side of the unit cell in terms of the radius. Okay, in terms of the radius of an atom. Because it's not 2r because there's this extra piece here.
I thought that you were just asking like what the radius is, and it would be 1.
Well, we don't, so it depends on what the atom is. The actual radius is whatever the atom is. Like, we have to look it up to calculate it. But it's going to cancel out. We'll get to that. So the diagonal here is 4r, 4 radiuses. So in Pythagorean's theorem, that's C. Right? This is A, this is B, that's C. So to get the length of A or B, they're actually the same. So I'm just going to replace this with, they're the same length. So it's just A squared, and A squared gives you C squared. 2A squared is equal to C squared. So I'm going to plug this in. I'm going to solve for A. That's going to be the length of one side. So I get 2a squared is equal to 4r squared. Alright, keep going. 2a squared is equal to, well, so 4 squared is 16, and r becomes r squared. Let's isolate and solve for a now. So I'm going to move the 2 over to the other side. That way I get a squared is equal to 8r squared. And then finally, square root of both sides. Square root of both sides, I get a is equal to square root of a, 8r. Alright, that was a lot of geometry, trigonometry I guess, to get that the length of one side of this unit cell, either side, is square root of 8 times the radius of whatever that atom is. Now let's calculate everything we need to know. We need to know what the area of the unit cell is. So the area of the unit cell is side times side, right? So a times a squared, so it becomes square root of 8 times r times square root of 8r, and I get 8r squared. That's the area of the unit cell. Okay, that's my denominator. That's the hard part. Let's do the easy part, the numerator. How many, well, so what is the total area of atoms that are inside the unit cell? So there's, how many atoms are there? Yeah, there's 2 atoms. There's 1 full atom inside the unit cell, plus a quarter, a quarter, a quarter, and a quarter. So there's 2 whole atoms inside the unit cell. There's 4 quarters plus a whole one in the center. So what is the area of an atom? It's still pi r squared. That's the area of a circle. But I have 2 atoms in there now, so it's going to be double this. So when I put everything together, there's going to be 2 atoms, 2 pi r squared. That's the area of the atoms inside the unit cell. And the unit cell itself is 8r squared.
Did you, I don't know if you made a mistake. Is it, oh, never mind, sorry.
Okay. Yeah, square root of 8 times square root of 8 just becomes 8. Yeah. And so now, r squared cancels out, and I'm left with 2 pi over 8, and I forgot to multiply by 100%. This will give me, if I do the math, let's see. Anybody wants to do it?
Because 1/4.
There's something wrong. Hold on. 2 times pi divided by 8 times 100 gives me 78.5%. So that's the packing efficiency for this particular arrangement of atoms. For some reason, it's almost the same as that one. But, you know, that's what it's saying. This unit cell is 78.5% covered with atoms and about 21.5% empty. So this is the kind of calculation we're going to do for 3-dimensional structures next. And it's a little bit more complicated. Yeah. So, I promise you we're not going to do this long derivation for the hard ones. Well, maybe we'll do some of it. But you don't have to know how to do this for an exam. This might be an extra credit question, but that's it. What we're going to do is use the equations that we develop. And I'll show you how that works in a little bit. But so that was 12b, or 15b, excuse me, calculate the packing efficiency of this arrangement. What was the coordination number of the central circle?
Is that one you're measuring?
Mm-hmm. Just 4, yeah. Every single central atom has 4. In fact, you don't even have to look at the central atom. You can look at the corners. And the corners are also touching 4. And that's going to be fairly, it's going to happen. You're going to see that pattern repeat over and over and over. Every single atom has 4 nearest neighbors. Okay. So, we're going to get to 3-dimensional stuff now. We have this framework with which to talk about them. So let's start off with solids in general. They can be crystalline, they can be amorphous. And it's actually surprising how often they're crystalline. Amorphous solids are things like soot, or wax, or plastic, or something like that. Most things are actually crystalline. They don't have to make gigantic crystals to be crystalline. They can be crystalline in really powder form too. So most ionic compounds are crystalline. Covalent compounds can be crystalline, like sugar. Even metals are crystalline. We saw that in the lab. And amorphous solids, glass and rubber, wax, plastics. Sometimes you can get plastics to have very regular structures, but not what we call crystalline. So anything amorphous has a disordered structure, okay? You can't use a unit cell to kind of say this is that pattern that repeats over and over and over. All right. So we're going to focus on the crystalline stuff because that's the stuff we can categorize very easily. And the crystal lattice, this is what we call the geometric arrangement of the, well, in this case they call it lattice points in a crystal. So this is the structure, the shape. Sometimes atoms will occupy those lattice points. Sometimes those lattice points will be empty. It really depends on the structure, okay? So when we describe a crystal lattice, what we're actually describing is just a simple arrangement, not necessarily of atoms, but just this theoretical arrangement of points in a three-dimensional structure. A unit cell is that smallest box-like unit, and it doesn't have to be a perfect cube. It can be any shape, and I'll show you. From which you can construct a crystalline base, stacking the units in 3 dimensions. And there are actually 7 different crystal systems. We are going to do 1, but there's like 7 of them that you can use to classify crystals. So here is a picture of all 7 of them. So we have the cubic ones, and that's the one we're going to focus on. The unit cells are length, width, height, all the same length, and the angles are all 90 degrees. Now the inside could be different, but that's the outside of the unit cell. That's kind of the shape of it. But you can have tetragonal, where one side is different from the others. So A and B are the same, and C is longer, but everything's 90 degrees. You can have them all different. A, B, and C are all different lengths, but they're all 90-degree angles. Then you can start having non-90-degree angles. And then you can start getting weird hexagonal shapes. Triclinic, everything's different here. So this is basically the math that goes behind talking about these shapes. These structures will guide you and tell you a little bit about their properties. We're going to focus on cubic, okay? Just cubic. That's it. And only a few of the cubic structures, too. Within these crystal structures, you can have more than one crystal lattice. Like I said, the corners, the outside parts have to be the same, but you can have other lattice points on the faces, on the edges, inside. You can have many different arrangements for each of these 7 crystal structures. The most primitive lattice of all of them is where there's only atoms at the corners. But you can have structures where there's, like I said, lattice points, atoms on the faces. You can have lattice points in the body, inside. And that's going to be reflected in their name. You'll see it. So we're going to focus on the cubic crystal system. So simple cubic, sometimes called primitive cubic, but simple cubic, SC, is the most simple one. You only have lattice points at the corners. So what does it mean to have lattice points at the corners? Usually it means you have atoms at the corners, and that's it. Okay. You can have something called body-centered cubic. And in this case, you have atoms at the corners, lattices points at the corners, but you also have a lattice point at the very dead center in the middle. A little bit like the 2D structure we just saw. This one's 3D though. And then the other one, FCC, face-centered cubic. You have, again, the corner lattice positions that define the box. But you also have a lattice position at each of the 6, in the middle of each of the 6 faces. Right? A cube is 6 faces, 4 all the way around, 1 on top, 1 on the bottom. So there's not something in the middle, not like body-centered cubic. There's just extra lattice points on the middle of the faces, not in the middle of the cube, middle of the faces. I'll show you those in a second. So here they go. Simple cubic, body-centered cubic, face-centered cubic. It's very difficult to show 3D in a 2D image, so they'll do perspective-like lines. This is trying to show you that it's in the middle. This is trying to show you it's in this space, in this space, dot, bottom. This is the front face, that's the back face. but nothing beats a real model. This is primitive or simple cubic, just atoms at the corners. That's it. This is body-centered cubic. Ignore the lines, right? You can't have something floating in there. It has to be connected somehow. So there's one in the middle, and I'll in case you don't mind touching them, hand them out. And this one's face-centered cubic. So we've got the corner atoms, and then we've got an atom in the middle of each of the 6 faces. Those are the 3 main crystal structures crystal units, cubic unit cells we're going to look at. And we'll see variations of these too. So it's not just going to be just that, but most of the ones we'll see will be based on these 3, okay? Yeah, don't feel like you have to take it if you're not a fan of it touching, coronavirus stuff, but it should be okay. Now, don't be lulled into thinking that the atoms have to look like that. Those are just points. Usually the atoms take up a lot more space. And so here's a better representation of what these unit cells really look like with atoms in them. And notice that when we did the 2D structure, we talked about, hey, this atom is only a quarter of the way inside the unit cell. Well, in 3D, it'll work out the same way. This atom is only a fraction of it is inside the unit cell. The rest of it is in neighboring unit cells. Okay? But look at this body-centered cubic. There is a whole atom inside that unit cell. With face-centered cubic, these are a fraction inside. That's only halfway in. You can kind of see that. And we'll see this more in detail. So whenever you see one of these, just don't think that that's the way the atoms actually look. All we're showing you is their positions, okay? That's it. They could take up a lot more room than you'd think. Now, how do we as chemists, who are not artists usually, draw these without having to, be 3D draw in 3D? We have these things called layer diagrams. And some people hate these, but what we do is we take slices of the unit cell and kind of draw what the slice looks like. And when we do layer diagrams, we only do enough slices to represent the unit cell. We don't. So for this particular shape right here, there's no reason to slice right through the middle because there's no atoms right through the middle. We only slice where we're going to go through a center of an atom. That's it. So what you're seeing here are the layer sequence. This is the layer diagram. And we usually label them going from Z is equal to 0. Z, the axis, Z-axis is the idea. Going from Z0 to Z1. So Z0 is the bottom of the unit cell. Z1 is the top of the unit cell. And if there's anything inside the unit cell that is interesting, we'll have fraction layers. 0.5, Z is 0.5, Z is 0.25. There's nothing inside these unit cells. There's only atoms at the corners, so we don't care about the inside. But you'll add as many layers as you need to show what's in the unit cell. Now, the unit cell, remember, how does it work? Every unit cell, the adjacent unit cell is exactly the same as the one right next to it. So if I take this unit cell and draw it right here, the top of this unit cell is going to be exactly the same as the bottom of the next unit cell. Is that right? Right? So this bottom layer, Z is equal to 0, is always going to be exactly the same as the top layer. So sometimes you don't even have to do 2 layers like this. You just do one. Z0 is the same as Z1, so you can do 0, 1, because they're always going to match. That's the idea behind a unit cell. Okay. So again, you only draw the layers where there's atoms that it'll go through the center of them. Okay. Yeah. 0, 1 and 0 and 1 are always identical. So, I think is that what we're going to do? Yeah. When we talk about the unit cell, let's make sure we're understanding the variables we're going to be using when we describe the unit cell with equations. R is always going to be the radius of the atoms that make up the unit cell. S is going to be the side of one unit cell, like the length of the side. And for us, since we're doing the cubic crystal system, they're all the same. It's a cubic unit cell, so length of the length and the height and the width are all the same. So we're going to look just at simple body center cubic and face center cubic, SC, BCC, and FCC. And I think this is not working, but let me check. Maybe it is. Oh, ads.
Good grammar and spelling are important, but if you want to write essays that
Sorry.
inspire,
Really, when did you see it?
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array.
Sorry.
Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and 1 in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above, and 4 more below, for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency,
All right, we'll stop it there because we're getting too much at this point. All right. Hopefully that was a nice little visual that maybe the models don't help with, but let's go through the activities on this page. Where is it? So this is page 34 to 35. I guess that would be 30, starting at page 30 in your thing. The questions start on page 32, and you guys are going to do questions 16 through 20. So I'll let you guys work on this one. This one's something easy. Let me see. Please refer back to this page because it's got a lot of equations on it. So you got different equations for the volume or the length of the side of the unit cell, I should say, based on the radius. needs help understanding question 18. Loan you these models here. This is the body-centered cubic unit cell. This is the face-centered cubic unit cell. Just kind of give you a better visual.
You don't come apart.
They don't come apart, no, but you can, so these are actually cut in layers. So you can see what the layer diagrams look like. So when you slice it where the atoms are.
Okay, so I'm trying to picture if I put for the, how many of these together, so there's 2, 4, and then the other are on the top.
Mhm.
Nothing. Okay, alrighty, thanks, we were magnetic.
Are they?
Are they not?
No, I don't think so.
What the heck?
They're 3D printed. Somebody made
Okay,
them.
well, that's my mind challenge on me.
You see 'em? So that's BCC, body-centered, that's face-centered. So this is actually an 8, because if let me imagine that this was, here's the neighboring one. I still need 1, 2 more, and then the top half. So there's 8 pieces to make a full atom. So that's why each one of these is 8 and 8. Oops. So every time you have a corner, these are always worth an 8. So even if they're small or big like this, it's still an 8.
And the reason is because it needs.
So let's see. Had a bigger one. Let's see. Think of it this way. So imagine this one right here. This is 1 unit cell. And there's an atom right there in the middle there. I think that's part of it. How many other unit cells are there that have this atom in it? Well, there's going to be 1 here, there's 1 here, and there's 1 in the corner here. That's 3 others. Plus there's the top layer. 1, 2, 3, 4. And so there's 8 total unit cells that share this atom. So each corner atom is always going to be an 8 inside 1 unit cell.
So because there's 8 units of the show.
Mm-hmm. And then for the FCC, the bases. See, there's this is half, and then the other unit cell is the other half. So they're shared by 2. That's it. All right. So visually, this is a little harder. It's going to be clear for some people. It's like some people see this better, easier than others. We'll go through them really quickly. Not really quickly, but we'll go through them, make sure everybody understands the answers to these. First, before we go through the answers, these examples of the different unit cells. So simple cubic, we saw the layer diagram for it. There's only 1, because slicing through the bottom layer is exactly the same as slicing through the top layer. So z is equal to 0 and 1 is the same. But for body-centered cubic, again, we only do slices where there's a center of an atom you can go through. And so here is the bottom slice, which is the same as the top slice, the same as the corners. And then there's 1 through the middle. And you can see that, hey, there's an atom in the middle. And if you need help seeing that, so here's body-centered cubic. You slice the top layer or the bottom layer, it's the same. You can see that fits just like that. And then when you slice through the middle, you get that picture. So there's 1 atom right in the middle. So that's the layer diagram for body-centered cubic. That's how you would draw it. You would draw 2 pictures. One looks like this. And you don't have to draw these outside atoms. You just have to draw the box. You can draw it like that. You can say there's atoms here. And then there's a second box, and let's label it, sorry. Z is equal to 0, 1. And there's a second box with an atom in the middle. Oh, and that's Z is equal to 0.5. We're slicing right in the dead center of the unit cell, halfway through. For face-centered cubic, there it is. And the layer diagram is a little bit more complicated because here's the top and the bottom. We have a face atom now right in the middle of that layer. And then when I slice through the middle of it, I get the 4 atoms that are in the middle faces of that, like, of the sides, right? So you've got the faces going around the sides, and I cut those in half. Those are those atoms there. So that's kind of what the layer diagram for FCC looks like. And again, you don't have to draw the outside part if you don't want to. You can just draw the unit cell part. Okay. Now, for the questions. Oh, here's a better picture. So somebody, if you're still unsure why every atom counts as an 8, well, here is a corner atom for that unit cell, the blue one at the back. That corner atom is shared by 8 different unit cells. There's the one in the back, that one in the back, the one in the front, this one in the front, and then the 4 on the bottom side too. So that one atom here on this corner is shared by 8 unit cells. So each unit cell gets 1/8 of it. So that's why corner atoms are only 1/8 inside every unit cell. And so when I add them up, 1, 2, 3, 4, 5, 6, 7, 8 corners, each count as an 8, they add up to 1 total atom. Okay? All right. So 17 is just copying those equations down. So I showed you how we derived one for 2D. You could do the same for 3D. It's just geometry and trigonometry, but we're not going to do that. So there it is. For simple cubic, the length of the side of a unit cell is 2 times the radius. I think that's clear to see. For body-centered cubic, it's a little more complicated to calculate. You got to do the diagonal thing with Pythagorean's theorem in 3D this time. Don't worry about that. That's the result. The length of one side is 4 over radical 3 times the radius. And for face-centered cubic, it just happens to be radical 8 times r. That's the length of one side of the unit cell with respect to the radius of the atom. All right. So we kind of answered 18. Why is only 1/8 of an atom at a corner? Why is only 1/2 of an atom on the faces? Well, here is FCC. You can see there's a face atom. Half of it, I mean, this is like half of an atom right here. Half of it is inside this unit cell. The other half is in the unit cell that is just directly opposite this one. So a face atom counts as a half. And there are 1, 2, 3, 4, 5, 6 faces. 6 halves is 3 total atoms. So being able to count the total numbers of atoms inside a unit cell is a critical skill for this class, okay? So how many atoms are associated with each unit cell? So 19 for simple cubic. How many are there? 1, yeah. So there's 8 corners. They're each count as an 8. So 8 times an 8 is 1. For body-centered cubic, 2, yeah. There's the corner atoms, which count as 1, is the center atom. And I think this was in the video anyway. But for face-centered cubic,
4.
yeah, that's it. All right, so far you guys are fine. All the corner atoms plus the faces. The faces count up to 3 atoms. The corner atoms count up to 1 atom. And that's it.
Sorry, why is the first one 1?
Because here's a picture of simple cubic. So this back corner is 1. And it's only, well, let's go to the original one even. There it is. The idea is inside the actual box, not the outside part. How many of those atoms are inside? Well, since the corner atoms are shared by 8 unit cells, then each atom is only 1/8 inside that single unit cell. So this atom is 1/8 inside this unit cell, this atom is 1/8 inside, and there's 8 total corners, so 8 times an 8 adds up to 1 total atom. So, I mean, this is not body-centered, but imagine imagine this thing in the middle wasn't there. There's 1, 2, 3, 4, 5, 6, 7, 8 1/8 pieces. So 8 times an 8 is they add up to 1 total atom. Does that kind of make sense? Okay. Yeah, there's 8 atoms on the corners, but only 1/8 of each of those atoms is inside the unit cell. Okay. So when you count up those pieces, there's 1 total atom overall inside the unit cell. And there it is. Here's a picture of it.
The reason the second one is 2 is because there's 4.
So there's the 8 corners, just like this one, there's 8 corners. These 8 corners count as 1 total atom, but then there is 1 in the middle too. And that's all the way inside. That's not shared by anything else. It's just inside. So there's 2 total atoms in this unit cell. Yeah, so there's a better picture of how to see what's inside the unit cell. And there is 4 total atoms inside this unit cell. Yeah, this is in your thing, it's just not colorized, unfortunately. Or maybe it is. Did you guys know? I don't think you guys know it. Alright. There are lots of online sources for this stuff too, so and I think there's some stuff you can play with, like with computer graphics, 3D stuff that you can scroll and zoom. Okay. Now, the last question, 20. For each of the 3 unit cells, what is the relationship between the radius and the volume? So, how do you calculate the volume of a cube? Perfect. And if they're all the same length, the length and the height and the width are the same, it's all S. We're going to call it S as the length. So the volume is S cubed, S times S times S, right? Length times width times height. So let's use this relationship to figure out the volume of each of the kind of unit cells in terms of the radius. Right? So, for this one, simple cubic, the length of a side is 2r. So what I'm going to do is I'm going to cube 2r to get the volume of that unit cell. So I get, what is 2 cubed? It's 8. And r cubed is r3, r to the power 3. So that's how I get the volume of that unit cell. It's 8 times the radius cubed. Alright, so for body-centered cubic, it's the same thing. I'm going to cube the side of a unit cell. Well, in this particular case, the side of a unit cell is 4 over radical 3r. So 4 over radical 3r. We're going to cube that. So you just cube every piece of it. 4 cubed, anybody know? 64. 4 times 4 squared is 16. 4 times 4 is 64. And anybody know radical 3 cubed? 27. If it was just 3, yeah, 27. But if it's radical 3 times radical 3 is 3. Times another radical 3 is 3 radical 3. It's so one of the radical 3's turns into a 3, or 2 of the radical 3's turns into a regular 3. Radical 3 times radical 3 is 3. Times another radical 3. There you go. It's it's annoying, but that's it. There he goes in the radius cubed. And then for our base center cubic, volume is, so how is the side related to the radius? Radical 8 times r. So I'm going to cube that. becomes 8 radical 8 r cubed. Alright, so there's your formulas for volume of a unit cell. It's not written down, it might be worth writing down. But you can transform these pretty easily. You just cube those to get the volumes. Alright, now what do we do with these? Well, we're going to do packing efficiency in a little bit. So, before we do that, we'll make sure how many atoms are found in the 3 different unit cells: simple cubic, body-standard cubic, face-standard cubic. Good multiple choice, quick answer test questions, right? I get this stick in your head. Alright. Oh, there's a weird delay there. Alright, so, yes, C. Okay, I got it to stick. Hopefully it sticks past today's lecture. So, let's now talk about, actually we did this one. So, question 20, these are the equations that we got for the volume of the unit cell. Now, let's do the remaining questions, questions 21 to 23. And we'll do these together because they are a little bit of a math nightmare. I wouldn't say it. They're not that bad, but it's easy to make a mistake. So, 21. Let's determine the packing efficiencies of each unit cell. So, the equation we're going to use for three-dimensional structures is very similar to the one we use for 2D. In the denominator, instead of the area, we're doing the volume of the unit cell. In the numerator, we're doing, instead of the area of the atoms, we're doing the volume of the atoms inside the unit cell. So the one geometric equation we're going to need is, what is the volume of an atom? And we're going to think of the atoms as spheres. So that's very simple. It's 4/3 pi r cubed. That's the area of a sphere. Okay?
What page is this on the RP?
Yours, I think it's 4 pages back, so it should be 32.
31.
31, sorry. It's not.
Oh.
Okay. So let's start with simple cubic. And so simple cubic, we're going to do well, we already have the volume of the unit cell. That's over here. The volume of a simple cubic unit cell with respect to the radius of the atoms is 8r cubed. So we need the numerator part. We need the total volume of atoms within the unit cell. Well, one atom has that volume. How many atoms are in simple cubic? Just one, right? We count up all the pieces, it adds up to one total atom. So for simple cubic, there's one atom, and that atom has a volume of 4/3 pi r cubed, and the volume of the unit cell is 8r cubed. Sorry. So the packing efficiency is going to be that numerator divided by the denominator times 100%. Notice that r cubed goes away. We don't care about the actual size of the atom, because the packing efficiency is going to be the same no matter what atom you use, as long as it has this shape, this arrangement. So 4/3 pi, 4 divided by 3 times pi, divided by 8 times 100 gives me 52.4% packing efficiency. That's pretty low. Only about half of that unit cell has atoms in it. Half of it's empty space. So that's the packing efficiency for simple cubic. Body standard cubic. The denominator is what is the volume of the unit cell for the BCC? It's 64/3 radical 3 times r cubed. What about the numerator? How many atoms exist inside body standard cubic? 2, yeah. And so if the volume of the atom obeys that formula, which it will, it's going to be 2 times that. Okay? And again, times 100%. Get rid of the radius cubed, they cancel. And now let's do this nightmare. 2 times 4 over 3 times pi. And then you're going to carefully do the bottom part. So 64 divided by 3 divided by radical 3. If I do this right, I get times 100, 68%. So body center cubic packs a little bit more tightly than simple cubic. There's less empty space. So that number is the amount of space that is occupied by atoms. So finally, FCC. How many atoms inside FCC? 4. And each one of them is a round sphere, so we're going to use 4/3 pi r cubed. The volume of FCC is 8 radical 8 r cubed. And then times 100%. And we're going to get, so radical 3 cancels out again. So 4 times 4 over 3 times pi divided by 8 radical 8 times 100, and I get 74%. So FCC is even tighter packing, like the atoms are trying to occupy as much space as possible and waste as little space as possible. There's less empty space. So, those are the 3 different crystal structures we're going to study in this class. These are the packing efficiencies. So now you can kind of gauge how much space they take up, how much empty space is there. Now, that so far so good? It's not too bad, right? Okay. Now, let's make it more complicated. 22. No, we did that one. No, we did 21. 22. If you were given the molar mass of the atoms that form the unit cell, how could you figure out the mass of the atoms within the unit cell? Anybody have a clue? Yeah.
Maybe see, like, the packing efficiency percentages and they have to add to 100, right?
Kind of. There's an easier way though. So what are the units of molar mass generally?
Grams or AMU.
AMU, but if it's molar mass, it's grams per mole, right? Usually per 1 mole. So it's whatever the molar mass or the atomic mass of the atom is per 1 mole. So what does 1 mole mean? It's a lot of atoms. Right. Right, a lot of atoms. But now we're looking at a crystal structure, unit cell. How many atoms are in them? Depends, 1 or 2 or just 4, right? So we could convert this to grams per atom, couldn't we? So how would I do that?
You would put 1 mole at the top and 6.022.
Exactly, Avogadro's number is 6. Sorry, get my number wrong. 6.022 times 10 to the 23rd. So I could get, and so this is the number per atom. This is the number of atoms in 1 mole. In this particular case, it could be anything, but in this case we're counting atoms. So I could divide any molar mass by Avogadro's number and get the mass per atom. Right? I get the mass of just 1 atom in grams. Okay? So that's how we do 22. Now let's use that and do 23. So 23, so here this is whatever it is. So 23, determine the density of lead. So we're going to calculate the density of lead using crystal structure techniques. That's it. We're not going to do it the normal way, which is to take a piece of lead, weigh it, and then calculate its volume and do mass over volume. That's the normal way to do it. We're going to do it using atoms and crystal structures. So, what we're saying is lead does an FCC unit cell. All right, so here's question 23. It's FCC, and the length of the side of the cell is 4.9505 angstroms. This might be a new unit for you. An angstrom is exactly 10 to the minus 10 meters. It's just a useful unit for talking about atom sizes. That's where it comes from. So, what we want to do is know the density of lead. So how do we get density? Well, what are the units of density that we are used to? Mass over volume, but particularly grams over what usually? Cubic centimeters? So we want to get something with those units. Now, I could take so let's think about it in terms of a crystal. Okay? I'm going to borrow this real quick.
So the people that are watching on YouTube can see what you're doing?
Yeah, they can.
They can? Oh,
Oh, they can't? Oh, here, let me. I can't see the questions though. That's the only problem. Let's see. Am I standing in front of it, or is it just got a weird reflection? It's not too bad. Okay. If you want to repeat their questions, that's fine. But I don't have time to look at the questions, so sorry.
Yeah, that's all he said, so.
Okay.
It looks like.
I think it looks okay. If they can't see it, it might be their bandwidth. Maybe they're getting like really blocky.
Oh.
Maybe force it to do HD if you can, and I don't know. It'll be recorded, and it'll be better recorded too, so you can watch it again afterwards. It may not be streaming well. That's all. Okay. So what I wanted to bring is this is FCC. Okay, this is an FCC structure. Let's think about what density is. Density is a mass divided by a volume. What if I could do the mass of the atoms inside the unit cell divided by not the volume of the atoms, but the volume of the unit cell? That's really what density is. So what I'm going to do is calculate the mass of the atoms inside the unit cell and divide it by the volume of the unit cell. I've had questions before, well, why not volume of the atoms? Well, if I did that, I would be super dense. Like, we have to include the empty space that the atoms don't take up as well. That's all part of the density. So I can do volume of the unit cell. That's pretty easy, right? What is the volume of a FCC unit cell? I erased it over here, but it's still over here. It's radical 8, or 8 radical 8 R3. That's the volume of an FCC unit cell. All right, so the volume is 8 radical 8 R cubed. What about R? Well, I've been given that. The length, or sorry, I haven't been given that. I've been given the, here, actually, we don't need this. I don't know the radius of the lead atom. But what they've been given is the length of the unit cell. So how do I get the volume from the length of the unit cell? Yeah, cubed. I just have to cube it, that's it, right?
You have to multiply it by 8 or 8.
Well, if I only have the radius, like the size of a lead atom, that's what I would plug in here. But if I have the literal length of the unit cell itself, so I have this length, I just need to cube it, and I'll get the volume of the unit cell. Yeah?
Should we put that in meters?
Yes.
Okay.
So I ultimately want in centimeters cubed. So actually, instead of meters, it'd be better in centimeters. So let's do that. I'm going to come over here. I'm going to convert the length of my unit cell from meters to centimeters. All right, so 4.9505 angstroms. And the conversion for 1 angstrom to meters is written right in the problem. It's 10 to the minus 10. But I don't want it in meters. I actually want it in centimeters. So let's convert centimeters to meters, or meters to centimeters, excuse me. And the conversion is 1 centimeter is 10 to the minus 2 meters. So I think if I do this right, it's 4.9505 times 10 to the minus 8 centimeters. That's the length of the unit cell itself. That's the length of one side here. So to get the volume, that's S, the volume is going to be S cubed. Just length times width and height, that's it. So if I cube that number, 4.9505 times 10 to the minus 8, let's see what I get. So 1.21 times 10 to the minus 22 centimeters cubed. That is the volume of the unit cell in centimeters. It's tiny, right? We're talking about on an atom scale. It's pretty small. So I've got my denominator for density. I've got the volume of the unit cell. Now all I've got left is the mass of the atoms inside. So, how are we going to do that? We're going to use this calculation up here. What is the molar mass of lead? It's 207.2 grams per mole. Well, I don't care about the weight of a whole mole of atoms. I want to know the weight of one atom. So I'm going to convert to grams per atoms. So 207.2 divided by 6.022 e to the 23rd. 3.44 times 10 to the minus 22 grams. So that's the mass of one lead atom per atom, grams per atom. But in an FCC structure, how many lead atoms are going to be inside the unit cell? There's going to be 4 lead atoms. So I'm going to take this number, multiply it by 4. That's how many lead atoms there are in the unit cell. So 4 atoms times grams per atom, they'll cancel out. I'm just taking a shortcut here. And then I'm going to divide this by the volume of the unit cell, 1.21 times 10 to the minus 22 centimeters cubed. And let's see what I get for an answer. So divide by times 4 and then divide by 1.21 e to the minus 22. I get 11.37 grams per cubic centimeter. That is my calculated density for lead based on crystal structure sizes. Like somebody went and measured the length of a side of a unit cell. We used the molar mass from the periodic table, and we were able to calculate a density from scratch. Let's see how well it agrees with the real value. Boom, 11.34. Pretty close. It's kind of neat. We can actually calculate a raw number like that from physical dimensions without, so before density was this thing that you had to measure it to understand what it is. Oh, metals have high densities, other things have low. Why? Well, now we're starting to understand why. It's how they arrange themselves into crystal structures and how they pack themselves. So if it was an FCC, if it was a different structure, what do we know about these different structures? Oh, I erased it already. But BCC has a less dense packing efficiency. It doesn't pack as well. Simple cubic is even worse. It's only like 50-50. So you'd have a lower density if that was the case. You have a higher density when you can pack a lot of metal atoms into a small space. And we can pack 4 lead atoms into this FCC volume here. And so that comes up with this density. pretty interesting, I think, that we can do this now. So, you know, this is one of the benefits of understanding crystal structure. Yeah, good question.
Can we expect a problem like this, say, in like a midterm or like even a quiz?
So, I think that calculating a density is something you should be able to do, yes. What you don't need to do is calculate the equations for FCC and simple cubic and BCC. So the equations that are on the previous page, these right here, these will be provided to you. So you don't have to memorize them, nothing. I'm not big on making people memorize equations. So you'll be provided these, and you just need to understand how to use them. That's it. But I think that a density question like this is, you'll practice this in the homework, and I think it's a valid one to get on an exam. Okay. Okay. Yeah, so it's pretty gnarly at first, but once you do it yourself, you'll be like, oh, it's not too bad. It's not too bad. All right. So, make sure everybody is clear on this. The packing efficiency, what is the order of packing efficiency? So you don't have to memorize these numbers either, but you do have to remember the order. So, in increasing packing efficiency, the order goes what? I apologize, people watching at home. I need like an assistant and a second computer to do like a professional streaming thing. It's kind of hard to monitor questions at the same time, especially when I have the regular class. All right. So yes, excellent. Everybody's understanding it. Everybody kind of memorized it so far. It's not too bad, right? You can kind of see it even. And these are the actual numbers. Again, you don't have to memorize them. If you need them, they will be provided to you. Yes.
Something I'm confused about is how, well, okay, I mean, it says that the packing efficiency for FCC, but we didn't calculate the packing efficiency. Oh, wait, yes, we did, I'm sorry. Never mind.
Yeah, okay, we did those three. And it's not necessarily that knowing how to do the packing efficiency is important. That might be an extra credit question, but just to understand what the difference between these unit cells are. They have different ways to pack, and you'll see some structures are more common than others in nature. So in fact, simple cubic is actually a pretty rare structure. There's not many things that will do that naturally, and that's because the packing efficiency is so low. It has to have certain conditions for it to do that. We're going to see FCC a lot, and bicenter cubic is another one that metals do a lot. Anyway, so we did that. And there's a lot going on here. Well, ultimately, instead of doing regular density, we're doing a special, I mean, it's the same density, it's mass over volume, but we're looking at the unit cell mass over the volume of the unit cell. That's it. We're just doing it on a really small scale instead of a large scale. So it's a different measurement, but it's the same units. Okay. Maybe I did a mistake on my calculations. I think I should have gotten better, closer to that. Maybe sig fig errors or something like that. Probably what happened. I'm not immune to those either, so. Okay. So make sure you can do that kind of calculation, that density calculation. So here is the calculation for the numerator part. All right, you start with a molar mass. You convert that to grams per atom instead, and then make sure you multiply it by the number of atoms in that unit cell. We did it a little separated here. We got the grams per atom, and then up here we multiplied it by the number of atoms in the unit cell. For the denominator, oh, and those are the units for it. works out. And for the denominator, read the question carefully. They might give you the side of the unit cell, in which case just cube it, so you got the volume. They might give you the radius of the atom itself. In that case, you'll have to use the equation for that unit cell. Like, how do you relate the side of the unit cell to the radius of the atom, things like that. So be careful what you've been given in the problem. All right. I want to go any further. No. All right. So, yeah. This is kind of what I was saying before. You should be able to do all of these things at the top. Density. You will practice that in homework, so give it a chance before. I mean, try that before you come and ask me about it. But, or you can ask me. That's fine. But the packing efficiency calculation that we did for the 2D example, that would be extra credit if I asked you about that. And calculating volume in terms of R. So in addition to those equations here, where you get the side of the unit cell, I think I would give you the volume of the unit cell in terms of R as well for those different things. So the ones that we transform these to volume, I would give you those as well. It's like just tedious work on an exam. You don't need to do that. Okay. So here, this is what I was talking about. What kind of metals take those structures? And so all the things in green are the body-centered cubic structure, naturally. The things in yellow, only polonium here does simple cubic. And then the ones in blue do face-centered cubic. And then there's other crystal structures we're going to ignore because it's just too much for this class. So that hexagonal structure, that weird one that we kind of saw a picture of, a lot of things do that as well. And there are others. So, you know, we did the 3 that we did because they're pretty common. The others are less common. We're going to ignore them. So if you want to learn more crystal structure, take a crystal structure high-level class. It could be a chemistry side class. It could be a material science class. Because this is a very engineering-oriented thing as well. Okay. Now, we've been looking at just metals, single atoms, occupying these lattice positions. And that's why we call those positions not atom positions, we call them lattice positions, because anything can occupy them. And in this case, what you're seeing is iodine molecules occupying lattice positions. So iodine is a molecular compound. It makes a molecule, I2. Well, that solidifies. How does that solidify? Well, it has to make a crystal structure. But it has to retain those little molecules. Those stay the same. And so these occupy lattice positions. I don't have a version of iodine, but I have dry ice. This is dry ice. This is frozen CO2. You've got your carbon, the black one. You've got your red oxygen atoms. And these molecules, I don't know if anybody can tell what crystal structure these occupy. Anybody tell from looking at this? This is one we've studied. So if I point to the carbons, I've got your 8 corners. And then these carbons are in the 6 faces. So the CO2s are all in FCC lattice positions. This is FCC. It's hard to see that because it's a little busy. But that is FCC. So even with, so that's why we call them lattice positions, not atom positions, because anything can occupy them to create that crystal structure. Okay. But this is iodine, and iodine makes crystal structures too. Even methane. We don't see this on Earth, but on the moons of Jupiter, I think, one of them, there's lakes of frozen methane. So how do you visualize that? Well, this is kind of what methane really looks like. It's CH4. Just pretend it's like a spherical object. That's what we're doing with crystal structures. So pretend it's spherical, and then you can see how it packs. What structure is this? Yeah, space-centered cubic. Yeah, it's got 8 corners, and then it's got face atoms inside, in between all the corner atoms. There's nothing in the center. You can't see it, but there's nothing in the center. It's just a face-centered cubic. So even nonmetals and well, let's see. Yeah, this doesn't actually show those. So let's talk about semimetals now. So covalent compounds generally are not solid at room temperature. Iodine was, but CO2 is not. You have to force it to become that. Methane is not. I mean, they form crystalline structures as well. It's not really represented on this. But let's now talk about the semimetals, because we've kind of started going over those compounds. What kind of structures do they make? They're a little bit funny. If you look at this chart, most of the semimetals have this hexagon pattern. And if you read what that is in the key, it says covalent network. So this is a special state for solids. It's not like metals where they are loosely bounded together. It's not like ions where the ions are just attracted to each other, but you can dissolve it in water and they'll split apart. It's not like CO2 where if you heat it up, the CO2 molecules will just fly apart pretty easily from each other, not disintegrate internally. But these semimetals do these covalent networks. So let's kind of examine a covalent network first. So let's talk about carbon. And carbon is not a semimetal, but it kind of is close. And it does structures similar to the semimetals. So we're going to start with carbon. And let's talk about like what kind of structure, what kind of characteristics carbon has, and what kind of structure would make from those characteristics. So they're not big, they're smallish, intermediate smallish, not super small like a metal, but they're in the middle. And carbon bonds, they are covalent generally, but they're not like super covalent, right? It's not like fluorine, which is super electronegative. It's electronegative, but it's closer to the semimetals. It's starting to get to the intermediate strength bonding, and because of the electronegativity. So when you talk about the nearest neighbor interactions, they're stronger than normal because they have semi-high electronegativity. The atoms interacting with its neighbors, they really want to steal electrons, they want to share them very, very strongly. And so bonding becomes directional, it becomes localized. When an atom sees a neighbor, it wants to share those electrons and not let them go. Unlike a metal, which everything's loosey-goosey, it doesn't matter. And so when you get to this state, you have fewer numbers of interactions they can have with neighbors. Metals can have interactions with lots of neighboring metal atoms because they don't really care about where they get their electrons from. They're not very attracted to electrons. But since semimetals and non-metals have, like carbon, are very interested in neighboring electrons, they can only have a limited number of nearest neighbor interactions. And so because of that, they form these really strong bonds with their neighbors that just kind of keep happening. So like one carbon will bond very strongly to a neighboring carbon, that neighboring carbon will bond strongly to other neighboring carbons, and this network of bonding is created. And it's a little bit different from nonmetals because of the difference in electronegativity. So carbon is a little bit closer, like I said, to the semimetals. Once you get closer to like what fluorine looks like, you get a little bit different bonding. And so this is kind of what happens. You get something like silicon. Silicon has 4 bonds. You can see that. And that results in having a coordination number of just 4. So this is a lot lower than the crystal structures we saw. So simple cubic has 6 nearest neighbors. Body standard cubic has 8 nearest neighbors. And if you need help seeing that, The body center cubic is over there. And you can just kind of look at the central atom. That central atom is closest to the 4 corners, or the 8 corners, excuse me. If you repeat this in 3D, even the corners have 8 nearest neighbors as well. Sorry, people on the screen here. So body center cubic has 1, 2, 3, 4, 5, 6, 7, 8 nearest neighbors. Face center cubic, this is a lot harder to see with 1 unit cell, but let's see, for instance, this face atom is nearest neighbor to these faces, these corners, and the faces on the unit cell right above it. So there's 12 nearest neighbor atoms for FCC. That's a lot harder to see. But I guess the important thing is, once you get to semimetals, the coordination number goes down quite a bit. So, how do you get crystal structures with only 4 nearest neighbors? The cubic lattices that we are looking at don't have those numbers. They're too high. So it's a little bit different structure. So let's look at diamond. And diamond does a similar kind of network that that silicon does. It turns out there are 4 bonds per carbon, and each carbon is arranged in a tetrahedral structure. So I've got a little really busy looking model of diamond right here. If you point at any one of these internal carbons, you can see 4 nearest neighbors, 4 bonds to a neighboring carbon. Ignore the out ones because this is the end of the unit, like the end of the structure. It keeps going. Every carbon has 4 bonds, and every carbon on the inside has a tetrahedral arrangement. Remember, tetrahedral is 109.5 degree angles everywhere. So how do we get that from our crystal structures that we've looked at? This is where it gets a little tricky to see. You have to start with an FCC cell. So this one here, this is FCC. This is FCC as well. And this one might be easier to see. But imagine you have the space-filling FCC. Everything is packed as tightly as possible. Remember, the packing efficiency is like 76%. There's very little empty space. Well, imagine that you physically remove the atoms of FCC a little bit outwards a little bit and made a little bit more room in the center. And so you get this next slide. Well, when you do that, you create space for more atoms. And those atoms have, or those lattice positions, I should say, have a name called tetrahedral holes. Right, that's what this TD thing stands for. These tetrahedral holes are called tetrahedral holes. First of all, holes, because when you move the FCC lattice positions apart a little bit, they create big holes. And they're called tetrahedral holes because every atom that's in a tetrahedral hole is nearest neighbor to 4 other atoms in this tetrahedral arrangement. Notice how many tetrahedral hole lattice positions there are. There's 8. There's 4 in the top quarter, and then there's 4 in the bottom quarter layer. All right, remember the layer diagram? This is our layer 0. This is layer 1 at the top. Halfway through is layer 0.5. So this would be like the 0.25, the quarter. This would be like 0.75, 3/4. And then you can fill that space back up. And kind of what these remaining pictures are kind of trying to show is that these new tetrahedral hole lattice positions, if I put an atom there, that atom will have 4 nearest neighbors, tetrahedral. But basically what I'm trying to show you is this is how you make tetrahedral structures. This is how you do diamond. So diamond, every carbon is nearest neighbor to only 4 other carbons. With plain FCC, just this, every nearest neighbor has, every atom has 12 nearest neighbors. That's too many for carbon. And so you have to modify this crystal structure. You have to expand the lattice positions, create these holes for new atoms to sit in. And there is another picture of this tetrahedral arrangement. So if you weren't convinced that this is a tetrahedral arrangement, you can spin this around and it looks like the standard tetrahedral, okay? So let's make sure, how many tetrahedral holes were there? There we go. All right. So there were, maybe somebody's, oh, I know what's happening. So there are 8 tetrahedral holes, okay? We're going to go back to that slide and show you that there's 8 positions. There's 1, 2, 3, 4, 5, 6, 7, 8. So it's like a spot for 4 in the top layer and 4 in the bottom layer. That's how many tetrahedral hole lattice positions there are. 8 in an FCC lattice structure. There's others. Now, confusingly, to make diamond, we don't use all tetrahedral holes. We don't need all of them. We just need half of them. So the diamond structure is almost the same as what we saw before. It starts with FCC. So there is a carbon in every lattice position on the FCC structure. We've got our corners. We've got our faces. But it's modified. We make some more room inside. We spread this lattice, this crystal structure out a little bit. And we only put a carbon in half of the tetrahedral hole lattice positions. So there's a total of 8 holes, but only half of them have a carbon in them. So there's 4 up here, and only 2 of them have carbons in them. There's 4 down here, but only 2 of them have carbons in them. That's it. That's the diamond structure. Alright, so after you've put them in and you've colored them all, they're all the same carbon, that's what you end up with. It looks like nothing, because it's 2D and it's flat and it's hard to see. But that's what this is. So, I'm going to pass this around. I want to make sure you can see it. You have the pink box right here is representing the FCC cube. So you've got your atoms at the corners, and if you look carefully, you can see the face atoms that make up the standard FCC. And then I want you to look inside the unit cell, and there should be just 4 extra atoms. There's 2 at the top, they have white tape on them, and there's 2 on the bottom side, and they kind of alternate. And that's it. That's the diamond structure. Yeah?
Is that why when it's cut it ends up like that and not like a square?
Sort of. So if you want to see how diamonds are cut, what you do is you look at the structure and you kind of angle it in a way where you could see a hole where there's no atoms. And that's kind of where they cut diamonds. They cut them along planes where there's like, you're not going to hit an atom. And there's lots of different angles they can take because of that, but that's how they cut them perfectly like that. They tend to cut along those planes.
But if they were all filled, would there not be? Would you change the?
I mean, if they're all filled, then it would be the wrong structure because the way this is set up. So again, the reason that it's set up this way is so that every single atom can only have 4 nearest neighbors. If you fill actually all the tetrahedral holes with carbons, then it would get too packed up, and some of the atoms would have more neighbors than they are allowed to have. So remember, carbon, this is one of the standard atoms we've worked with in the past. It only wants an octet. It can't have more electrons than 8. And so you can only bond 4, it can only have 4 bonds, that's it. Carbon's pretty normal in that regards. And so it can only have 4 nearest neighbors, and that's it. Metals can have more because of the way metals work. But carbon can only have 4 bonds, and so it has to have this structure in order to have 4 nearest neighbors, and that's it. Yeah?
So even if it's cold, it's.
Oh, if it's cold.
What if it's different? What if, yeah.
So coal, well, I don't know know the structure of coal too well. I think it's more like soot. It's more amorphous, where there's not a regular structure. And I'll show you graphite now. So this is graphite. And I don't know if you can see, there is no atoms between like layers. Graphite makes layers like this. If you actually get a block of graphite, you can put a piece of tape on it and peel away a really thin, super thin layer. And that's because it's the structure like this. If you look, it looks like the carbons all have 3 bonds, but they all have 4. There's double bonds in there that make the 4th bond. But this is just another form of carbon. It's an allotrope, they call it. So different ways that they can arrange themselves. But that's diamond, and that's how diamond works. That structure makes it the hardest structure on Earth. It's like you can't scratch a diamond, but you can use diamond to scratch anything else. Yeah, I don't know if I can say anything else. I mean, so the takeaway here is, it's not more of a, it's more of a, like, why does diamond have this shape? Well, this is the shape that gets it for coordination number 4. Every atom is near 4 other carbons. Yeah.
And then you said make diamonds. So this structure doesn't form naturally?
It forms under high pressure. So it's not. I'm trying to remember. I believe that the lowest energy form of carbon is graphite, but you can form diamond under extreme pressure. So, like, you can make them in a lab using pressure. You can make them in a lab. There's some fancy techniques for making diamonds as well. But yeah, if you just tried to do a reaction that made carbon, it would make soot usually. Like, so burning anything, burning gasoline with a bad mixture of oxygen, an imperfect reaction, makes lots of soot, just plain carbon that has no structure at all. Yeah.
But like, so what does the pressure? How does the pressure really get those carbon atoms in those like specific tetrahedral holes?
So it's. I guess it's a. So the nature of matter, like matter in the universe, wants to be in the lowest energy state possible, right? So we're not going to talk about entropy in this class, but the natural state of the universe is to become more disorganized. This is the opposite of that. This is more organized. So this is already going against entropy. So you need to add energy into it to make this structure. It doesn't form. I mean, it forms naturally, but only under extreme conditions. So buried way under the earth with lots of weight and lots of pressure over a long, long, long period of time. Yeah, so it's stable. Once you can form it, it's stable. Carbon is happy with 4 bonds, but it is not the most stable form. Like, you can easily burn diamonds. You can react them with oxygen and ruin them. But as they are like this, they're hard. That's just the way it works. Yeah. Okay.
Can you tell us
Yeah. Go ahead.
what's like gonna be on the quiz?
Oh, yeah, we're almost done. Let's stop here. So, on the quiz is just going to be 22 through 24. None of the new stuff. So 24A, none of that.
So just like
So the stuff that was on the homework.
a lot
Yeah.
of it was like on table and stuff. So do we have to like? I feel like a lot of it is like we need to know the range of like what's metallic and.
Well, you should know generally where metals fall, where non-metals fall. I will give you the bond type triangle, like I said, without any labels on it. So you'll have the triangle, you'll have the axes, and you'll have the lines that mark off the regions. But the regions won't be labeled, the ends won't be labeled, you just have to know what they are. And as far as electronegativities go, I'll give you the electronegativity values if they're needed for the problem. But otherwise, a lot of it you can just kind of get from trends in the periodic table. What else can I say about it? Yeah, it's kind of why I asked if there's any problems with the homework. It's, you know, if the homework made sense to you, you'll probably be okay with this. If you understand how to work with the bond type triangle, that's good. If you know how to, what else is there? You know how to gauge ionic bond strengths by what the atoms are, like what the charges are, how big the atoms are. You're good. If you know how to, what else is there? That's 23. Oh, metals. So understanding the structure of metals, not this stuff, but like how do you visualize metals? Think of them as these nuclei with some electron, like cations with electrons that are just free to go wherever they want. That's what metals are. Even though they're neutral, their valence electrons are loose and they're allowed to go anywhere, and that's what makes them conductive. Just kind of the difference between a metal and a non-metal based on electronegativity. So around 2, that's where you get the semimetals. Below 1.8, that's metals. Above 2.2 or so is about non-metals. Anywhere in that range between is a semimetal. And then bond type triangle stuff. That. And then all the bond type triangle stuff. So being able to take the change in electronegativity and the average electronegativity and tell me what kind of bonding is present. So yeah, if you need to know electronegativities, I will give them to you. You don't have to memorize any of these, but you need to know how to use them to calculate change in electronegativity, average electronegativity.
Right, but we do need to know like the range of what is metallic and what's like ionic.
No. So on the bond type triangle, like I said, I'll give you the outline. So, you know, you'll have the axes, they'll be labeled. You'll have the triangle on there that has the lines on it. I just won't label anything. So you'll have this with the axes will be labeled, but there's nothing else. Does that make sense? So you'll know, hey, it's over here, so it's what's this region? And it's over here, what's this region? It's right on the line. It's between this and this. What are those two regions? Okay? All right. Okay, so let's stop there, and we'll pick up structures on Wednesday after the quiz. We'll do the quiz first. The structures thing, there's going to be a whole lab dedicated to it. So if this is like, you just can't see it, we're going to try to get it into you some other ways, like using computer models, using actual, I think we'll build structures using marble, like not marbles, but we've got these fancy crystal structure kits. They're kind of fun. And it's like they're physical balls that will fit together in a certain way and not in other ways, and you're like, oh, that's what the structure looks like, and you'll build unit cells. Pretty neat. Okay. All right, let's stop there. Sorry to take you over time a little bit. Feel free to come and look at these models if you haven't had a chance to. And sorry at home, guys. This is a class that's so much better in person. I know today was a unique day. So let me know if the recording doesn't work. But that's what I can do right now.